Hello dear students, today's lesson we're going to solve the questions of section review in section 3 and all questions in a standardized test brief of chapter 6. Question 1 in section review 3.6, the RMS current that a single coil of an electric guitar produces is 0.025 milliampere. What is this? This is the RMS current. What do you mean by RMS? It means that effective value. The effective value of current is given in this question. I effective is equal to 0.025 milliampere. The effective current is given in milliampere, so that is why we have to convert to ampere, multiply by 10 power negative 3. I effective is equal to 0.025 times 10 power negative 3 ampere. This is the RMS current of a single coil of electrical guitar. The coil's resistance is 4.3 kilo ohm. What is this? This is resistance. But the resistance is given in kilo ohm. We have to convert kilo ohm, convert to what? To ohm. Okay, so you have to solve the question with the SI unit, not with the prefix. How can you convert kilo ohm to ohm? Multiply by 10 power 3. Okay, 4.3 times 10 power 3 ohm. Okay, what is the maximum instantaneous current? What is unknown? The maximum instantaneous current, which means that IM is unknown. And what is the RMS EMF produced by the coil? What is the RMS EMF? What do you mean by RMS EMF? It means that effective value of potential difference, VE. What do you mean by RMS EMF? It means that V effective, the effective potential difference. And what is the maximum value of the potential difference? VE, VM, unknown. Okay. First of all, we have to find the maximum instantaneous current. How can you find the maximum instantaneous current? I maximum is equal to I effective times radical of 2. Okay. Do we have I effective? Yes. Was given 0.025 times 10 power negative 3 times radical 2. The RMS current is equal to 3.5 times 10 power negative 5 ampere. 3.5 times 10 power negative 5 ampere. Okay. For the second unknown, the effective value of potential difference, V effective. As you know, V effective is equal to find V effective is equal to Vm over radical 2. But we cannot use this equation. Why? Because we don't have maximum value of potential difference. That is why we cannot use this equation. So we have to think about another equation according to Ohm's law. V effective is equal to I effective times resistance. By rearranging this equation, without rearranging, just replace I effective. Do we have effective value? Yes. 0.025 times 10 power negative 3 times resistance was given 4.3 times 10 power 3. So the effective value of potential difference is equal to 0.11 volt. What is this? This is the value of effective potential difference. So the last unknown in this question, the maximum value of potential difference. To find maximum value of potential difference, there is a relation. VE is equal to Vm over radical 2. Rearrange equation. Vm, VE times radical 2. Do we have VE? We didn't have, but we found it. It was 0.11 times radical 2 is equal to 0.15 volt. Okay, so this is question 1 in section review, section 3 in chapter 6. Okay, question 2. Why do we charge a capacitor under a DC voltage source only? The capacitor can be charged under DC voltage. Why? Because in DC voltage or in DC source, the current flows in only one direction, and the current at its maximum value always. Okay. For example, if we connect a battery with a capacitor, so this capacitor becomes charged. Okay. This capacitor becomes charged under DC source. Okay. So the negative charge will accumulate here, and the positive charge will accumulate here. We can get a permanent capacitor. Okay. So why this is DC source? Why the capacitor charged only by DC source, not in AC source? Because in AC source, the current has maximum value only at one instant. So the current becomes zero maximum. Okay, so that is why under the AC source, the capacitor can be charged, discharged, charged, discharged. Okay, but in DC, it's not like that. In DC, the capacitor will be charged for a short period. Okay, so the current in DC is like that. Okay, has only maximum value, but in AC source, as you know, the current the magnitude and direction of the current changes. What is the value of current here? Current 0, but here maximum. So at this point, the capacitor becomes discharged, but at this point, the capacitor becomes charged. So that is why, because the capacitor charge and discharge periodically by what? By alternating current. Or because the magnitude and direction of AC current is changing, causing the charge and discharge the capacitor at the same time. So the DC current is suitable to charge the capacitor. Okay, so it means that the capacitor can be charged only under DC source, not AC source. Why? Because in DC source, the magnitude and the direction of the current does not change. The capacitor can be charged. But in AC, because the magnitude and direction of the current changes from 0 to maximum, maximum to 0, that is why this capacitor becomes charged, discharged, charged, discharged, and that is why we cannot get advantage or benefit from this capacitor. Okay? Question 3. The last question, critical thinking. What is the average value of current over one cycle? Over what? Over one cycle of an AC signal. Okay? So why then is a resistor heated by an AC current? So this question has two parts. To solving the first part, what is the average value of current for one cycle? The average value for current over one cycle. This is half cycle and this is one cycle. Okay? The average value of the current for one complete cycle is equal to 0. I average is equal to 0. But why? For example, the magnitude, the value of the current here is 0 ampere, and assume that here positive 10 ampere and here negative 10 ampere. Okay? To find the value of the average current, I average is equal to I1 plus I2 divided by 2 is equal to 10 plus minus 10 divided by 2. 10 plus minus 10 is equal to 0 divided by 2, 0 ampere. What is this? This is the value of average current. The average current over one complete cycle is equal to 0. Okay? The second part of the question, Why then is a resistor heated by an AC source when the average value of the current is 0, but the wire still heated? Why? Because this is the answer of the first question. Average value of current is 0. The current is positive for exactly the same amount of time that is negative. Okay, for example, if the current has positive 10 ampere, also it has the negative 10 ampere in another direction. So the direction of the current, positive or negative, does not affect the heating of the resistor. Why? Because the heating of the resistor, depending on what? Depending on the power dissipation, P is equal to what? Is equal to I effective square R. Which type of current can be used for power dissipation or for energy losing? The effective value of the current, not average value. Okay, so why the wire becomes heated or warmed? Because the losing energy or power dissipation or heating of the wire does not depending on the direction of the current. It depends on the magnitude of the current. Which magnitude of the current? The effective value of the current. Okay, so that is why the resistor is being heated throughout the cycle, wherever the current is positive or negative. Why? Because power dissipation, the power that converted electrical energy to heat, is equal to I effective squared R, not I average. Okay? This is the last question of section review. We finished the questions of section review. Now, let's solve the questions of standardized test brief. Standardized test brief of chapter 6. Question 1. Which of the following equations correctly describes Faraday's law of induction? As you know, Faraday's law of induction is equal to EMF negative N change flux over time. Okay, negative N delta flux is equal to what? AB cosine theta divided by T. Okay, the first one is wrong. Why? Because this is not tan. The second one also is wrong. Why? Because there is no negative here. Okay, and C is correct. Why? Because already we have negative N and change in AB cosine theta over time. D is wrong. This is not the Faraday's law for the induction. Okay, this is question 1. Question 2. Question 2 is very good question. Be careful, please. Pay attention. For the coil shown in the figure below, what must be done to induce a clockwise current? So what must be done for what? To induce what? The clockwise current. Okay. So in that case, we have a coil. Okay. And the coil is wrapping like that. Okay. And sorry. Okay. How can we get the clockwise current, induced current in this figure? Either move the north pole of magnet down into the coil or move the south pole of the magnet up and out of the coil. Either what? Move the north pole of a magnet down into the coil. For example, if you have a magnet, north-south. In the case when we move the north pole of a magnet down into the coil, so in the case of approaching north pole, this end also becomes what? North. This end becomes south. By using the right hand rule for the solenoid, you can find the direction of the current and the magnetic field. Now we know the direction of the magnetic field. The upper, it becomes north. Okay, so the direction of the current is not clockwise. Here is clockwise. Okay, so that is or move the south pole of magnet up and out of the coil. So it means that in the case when we move away the south pole, Okay? Move the south pole of the magnet up and out of the coil. Out of the coil, it means that moves away. In the case of moves away of the south, also this end becomes north. So which means that A is wrong. Why? Because in the case when we move the north pole of a magnet down into the coil, the direction of the current becomes counterclockwise. For the first one, the direction of the current is what? Counterclockwise. Okay? Counterclockwise. But the question asks us to find the induce a clockwise current. B. Either move the south pole of magnet down into the coil. Move the south, and here this is north, okay? In the case when move the south pole of magnet down into the coil, approaching south, this end also becomes south, this end becomes north. In the case when this end of this coil is south, the direction of the current becomes what? They enter here, they become as clockwise. Okay, becomes what? It becomes clockwise. Let me draw another figure. So the figure should be given in this question. In the case when we move down the south pole, this end also becomes south and this end becomes north. The same thing in the case when we move up or either move the north pole of the magnet up and out of the coil. In the case when the north pole moves away from the coil, also this end becomes south. So when does this end become south? In the case of approaching south pole, or in the case move away the north pole. When this end is south, by using the right hand rule, this end becomes north. Okay, so that is why the direction of the current becomes like that. So this is clockwise induced current. So that is why B is correct. Okay. Question 3. Which of the following would not increase? Would not, please be careful. Not increase what? The EMF produced by a generator. EMF produced by generator. I suggest for you to write down the equation of EMF for generator is equal to NAB omega sine omega t. Which of the following will not increase? Rotating generator coil faster, it means that omega? No. By increasing the omega, the EMF increases. So that is why A is incorrect. Because this question said which of the following would not increase? By increasing omega, the EMF will not increase? No, it will increase. B, increasing the strength of the generator magnet, increasing magnetic field. So by increasing omega also it is increasing. By increasing magnetic field also in this EMF increases. So that is why B is also is wrong. Okay? By increasing B, the EMF will not decrease, will increase. C, increase the number of turn. By increasing the number of turn, the EMF produced by generator decreases? No. By increasing number of turn, also EMF increases, because the EMF in generator depends on 4 factors or 5 factors. Number of turn, area of the coil, magnetic field, angular speed, and the orientation of the coil in the magnetic field. Okay? The last one, D, reduce or decrease the cross-section area of the coil. By decreasing cross-section area of the coil, is the induced EMF decreases? Yes, absolutely. Okay, so that is why D is correct. Okay. Question 4. By what factor do you multiply the maximum EMF to calculate the RMS EMF? By what factor do you multiply what? Maximum EMF to calculate what? RMS. So which means that we have to use the RMS value. IRMS or effective is equal to what? Is equal to IM over radical 2, which means that I effective is equal to, you can take out IM here, IM of 1 over radical 2. So by multiplying IM by which of the following for getting the effective value of the current, multiplied by 1 over radical 2. By what factor do you multiply the maximum? By what factor? By what factor do you multiply the maximum current? To calculate what? The RMS current or alternating current. The correct answer is what? 1 over radical 2. This is question 4. Question 5. A coil is moved out of the magnetic field in order to induce an EMF. Okay? A coil is moved out, the relative motion between coil and magnet, in order to what? Induce an EMF. The wire of the coil is then rewound so that the area of the coil is increased by 1.5 times. So which means that EMF for the first time is equal to what? Is equal to negative NA cosine theta delta B over delta T, okay? N1 A1 B1 T1, okay? In this question, the coil is then rewound so that the area for the next time, the area of the coil is increased by 1.5 times. What do I mean by that? It means that A2 is equal to 1.5 times of A1. It means that the area of the second time, the second rewound of the wire, bigger than for the first time by factor of 1.5. Extra wire is used in the coil, extra wire, more wire, so that the number of turn is doubled. What happened to the number of turn? N2 is doubled, twice as much of the first time, 2N1, okay? If the time in which the coil is removed from the field is reduced by half, the time is reduced, okay? Area increased, number of turn increased, but time T2 or delta T2 is equal to half of T1 from the field is reduced by half. What do you mean by half? 1 over 2, okay? So the magnetic field strength remains unchanged. The magnetic field is what? Remain unchanged. B doesn't change. B1, B2 is equal to B1, okay? What is the unknown in the question? How many times greater is the new induced EMF than the original induced EMF? So we have to find the ratio between what? E2 over E1 or E1 over E2. For the second one, for the second time, E2 is equal to what? Is equal to N2 A2 cosine theta B2 over T2. For the first one, for the first time, N1 A1 cosine theta B1 over T1. Okay? E2 over E1 replace. N2 becomes doublet. Instead of N2, negative with negative cancel. Instead of N2, write what? 2N1 times. Instead of A2, 1.5 A1. Cosine cancel. B is equal to 1. Okay. So 1 over, because doesn't change. T2, 1 over 2. Okay. In the denominator, A1 is equal to N1 A1. Okay. This is 1 over 2 T1. Okay. N1 A1 times 1 over T1. And you can write B cancel, T1 cancel, A1 with A1 cancel, N1 with N1 cancel. So what is remain? What is remain? E2 over E1 is equal to what? The denominator becomes 1. So 2 times 1.5, 3. 3 times 1 over 0.5 E2 over E1 becomes, so 1 divided by half is equal to 2. 3 times 2 becomes 6. 6 over 1. So which means that E1 is bigger than the E1 by factor of 6. So the second EMF, induced EMF, is bigger than the first EMF by factor of 6. Why? Because number of turn increases and the area also increases, the time is decreasing. So the EMF directly proportional to the number of turn and the area. By increasing number of turn and the area, also the EMF increases. But relation between induced EMF and time is inversely proportional. By decreasing time, the EMF increases. Okay, so that is why the correct answer 1.5 times no, 2 times sorry no, 3 times no, 6 times. Okay, I prove it for you. So this is question 5. Very good question. Be careful. Okay. Question number 6 from standardized test prep also is a very good question. Pay attention, please. Listen carefully. Question, use the passage below to answer question 6 and question 7. So it means that the question 6 and question 7 related with this figure. A pair of transformer, which means that we have 2 transformers. How many transformers do we have? 2. Connected in series as shown in the figure below. How many transformers do we have? We have 2 transformers, okay? But I don't know which one the first transformer and which one the second transformer, okay? Question number 6. From left to right, which means that from this side, okay? From this side, left to right. What are the types of the 2 transformers? How many transformers do we have? 2. From left to right, what are the types of the transformer? For the first transformer, this is N1, this is N2. For the second transformer, N1, N2. First one, which one is bigger, N1 or N2? Absolutely N1, okay? N1 bigger than N2. When N1 bigger than N2, what is the type of the transformer? Step down. The first one is what? Step down transformer. What about the second one? The second one, N1 also bigger than N2, which means that the second transformer also step down. So the correct answer, both are step down transformer? Yes. When from the left to right, when we see from left to right. But in the case from right to left, the 2 transformer becomes what? Becomes step up. Be careful. Maybe they will bring in the exam like that. What are the types of the 2 transformer from right to left? From right to left, which means that from this side. From right to left. The first one, step up. The second one also step up. Okay, but in this question, from left to right, both transformers are step down transformer. Okay, this is question 6. Question 7. What is the output potential difference from the secondary coil of the transformer on the right? Okay, what is the output potential difference? V2 is unknown for the second transformer. Okay, so in this question, to find V2, we have to use this equation, V2 over V1, N2 over N1. Okay, do we have V1? No, V1 is not given. Without V1, the input value of potential difference in the secondary transformer, how can you find potential difference? It's impossible. We cannot find. Okay, but do we have number of turn? N1 for the second transformer? Yes, 600. Do we have N2? Yes, 20 turn. Okay, but we don't have V1. Okay, how can you calculate V2? By the information and the given value of the first transformer, you have to find V2. So V2 is equal to V1. Look, so what is the important here? In this question, how many transformers do we have? We have 2 transformers. the output potential difference for the first transformer has the same value of input potential difference for the second transformer, which means that V2 first transformer is equal to V1 second transformer. The output potential difference V2 of first transformer is equal to the input value of the second transformer. So could you find V2 in first transformer? Yes, because V1 is given, N1 also is given, N2 is 57 also is given. So that is why this is for the second transformer. Second transformer. But now we have to find what? We have to find V2 is unknown for first transformer. Okay, V2 over V1 is equal to N2 over N1. Okay, rearrange equation. V2 is equal to what? V2 is equal to N2 times V1. Replace. Do we have N2? Yes. 50 times and V1 was given 240,000 volt divided by number of turn in primary coil also was given 1000. Okay, so V2 is equal to, by calculator you can find V2 is equal to 12,000 volt. What is this? This is V2 in first V2, the output potential difference for the first transformer, which is equal to what? The input value of V1. Okay, so which means that V1 is also 12,000 voltage. Why? Because the output potential difference for the first transformer becomes the input potential difference for the second transformer. Now we can replace into this equation. Okay, replace into this equation to find what? To find V1. V2 is unknown from this equation. Okay, V2 unknown, V1 we didn't have but we found it, is equal to N2 in secondary transformer 20 divided by N1 60. Okay, so V2 is equal to what? 20 times 12,000 divided by 60, which is the output potential difference for the second transformer is equal to 400 volt. Is equal to what? 400 volt. In both cases, the transformer are stepped down. Why? For the first transformer, what was the value of input potential difference? 240,000 volt. But its output is 12,000. So that is why it is stepped down. For the second transformer, what was the input potential difference? 12,000, which is stepped down to 400 volts. Okay, so this is question 6, a very good question. Be careful, please. Okay, question number 8. The maximum values for the current and the potential difference in an AC circuit is 3.5 ampere and 340 volt. What are these two values? The maximum values. Okay, which means that IM is equal to 3.5 ampere. Vm is equal to 340 volt, respectively. How much power dissipated in this circuit? So what is unknown? The power dissipate. P lost. P lost is unknown. To find P lost, which value can be used to find P lost? To find power dissipation, we have to use the effective value. We have to use what? The effective value of potential difference and the current. So, sorry, but in this case, the power dissipation. So, P lost for what? P dissipate in circuit. In this circuit. So this is completely different with the power dissipation through the wire. So this is the power dissipation in the circuit. So that is why we have to use this relation. Power dissipation in the circuit is equal to IV. But which value can be used? The effective value. To finding the power dissipation through the circuit, it's not allowed to use the maximum value of current and potential difference. To find the power dissipated in the circuit, you have to use the effective value of potential difference and current. P is equal to. Do we have I effective? No, but I effective is equal to Im over radical 2 times, instead of VE, write Vm over radical 2. Okay? Radical 2 times radical 2 is equal to 2. So Im times Vm remain. Replace 3.5 times 340 divided by 2. P is equal to what? Is equal to 595 watt. Approximately is equal to 600 watt. The correct answer is what? 600 watt. But actually by calculator, you will get 595, not 600. But in this book, it's written 600 watt. They rounded up to 600, okay? In the short response, we have some questions. The alternating current through an electric toaster has maximum value. This is Im, 12 ampere. What is the RMS value of this current? It's too easy, just replace. IE is equal to Im over radical 2 is equal to 8.48 ampere. What is the purpose of the commutator in an AC generator? The commutator in AC generator converts AC generator to DC current in one direction only. Okay, so this is AC generator produces an alternating current, but this is AC. Okay, but in DC generator with a commutator, only the magnitude of the current changes. So this is DC pulsating. Okay, what is this? DC pulsating. By using many loops and many circuits, this pulse decreases and it becomes a little pulse. Okay, a transformer has 150 turns of wire on the primary coil, which means that N1 is equal to 150 turn in the primary coil and 75,000 turn on the secondary. N2 75,000 turns. So which means that this type of transformer is step-up transformer. How did you know? Because N2 is bigger than N1. If the input potential difference, what do you mean by input potential difference? V1 is equal to 120 volt. What is this? This is the input potential difference. What is the output potential difference across the secondary? V2 is unknown. By using this equation, V2 over V1, N2 over N1, okay? And V2 is unknown, V1 was given, N2, 75,000 divided by 150, so V2 is equal to 6 times 10 power 4 volt. Okay, this is question number 11 from the short response, and the extended response is skip it, not included for the general exam. Thanks for listening. We finished chapter 6. Hope you enjoyed and get benefits from my lessons. Thank you very much.